Hello, I am Dr. Paris R. von Lockett, and today we'll be talking about contact stresses. Usually a pretty advanced topic in solid mechanics, but we need to understand them a little bit so we can understand how to apply them in SolidWorks and what some things, interesting pieces of our results might show. So this lecture focuses on understanding the fundamentals of contact stresses, also called Hertzian stresses, based on who first derived them, in rolling or no-slip static conditions. That means we have two surfaces that are in contact with each other, but they're not translating relative to each other. They are directly in contact with no slip or relative motion between them. The topics for this lecture include Hertzian contact stresses, as I've said, the stress values that occur from these contact stresses at the surface, and also subsurface stress phenomena, which is sort of the interesting part. After this lecture, it's important that you're able to compute the average and maximum stresses given input conditions. So if you have all the forces and you know the contact area, can you calculate those things? Also, to understand the importance of subsurface stress phenomena and how that can lead to surface evident failures, and to understand that contact stresses create a three-dimensional stress state. So yes, we have one body pushing down against another. It seems like it's one-dimensional, but the stress state that it creates is actually 3D. All right, where are we at in the course sequence? Well, in terms of our fundamental engineering concepts, like I've said before, we've gone from our introduction to beams, to stress concentrations and multi-axial stresses with our C-shaped clamps and our curved beams. And now we're here at this problem of working with pliers. And we'll show you more about that in the application packet. But the pliers problem is interesting because we have a real device. It's a device that's made up of multiple SolidWorks bodies. They move relative to each other through this pin here. They're loaded on a grip or the handle, and then they act on this little small fork, which you also have to design because it's the thing that the pliers are contacting. SolidWorks has this functionality. It's pretty well built in. There are a few different layers to it that we'll talk through how to apply those conditions, and then in this application packet you can get started working with it on your own. And of course, this is all building to the homework assignment, which involves doing the same thing with a different geometry, but similar geometry. So why do contact stresses exist? Well, they exist to equilibrate the load between two bodies whose surfaces touch. And I should put the caveat to deforming bodies. So imagine you have two things that come in contact with each other. At the instant they're in contact, there's only a single point of contact, but as that contact increases, they may deform, flatten out, and the surfaces that touch get larger and larger, and that's pretty much what's shown here. The result of two contacting surfaces is what's called a contact patch, and as they deform, this patch gets larger. Now, if they're elastic at all, then you know that there's a stress versus strain response that's going on. So the more they deform, the higher the stress level, and the higher the stress level, the more stress that they produce. So that larger stress is exerted over a larger area, so the amount of force resisting that contact increases, and that's where our equilibrium comes from. Whatever the forces are acting on our two bodies puts them in contact, and once that contact area is large enough and the stress levels are large enough to equilibrate those external forces, then the contact area stops growing and they're in equilibrium. All right, analytically, what we do is we model this as a semi-ellipsoidal pressure distribution over the contact patch, and that allows us to neatly perform some integrals so that we can equilibrate or balance the load in that contact patch with an external load and then transfer it from one body to the next. As you might imagine, if you can think through this visually, spheres will have a circular contact patch because if they deform uniformly, then the sphere will impact a circle. Other geometries will have different shapes. And so as a general rule, we can say we model these as either ellipsoidal or for some geometries as rectangular. Contact stresses were first developed analytically by Heinrich Hertz in 1881, so a long time ago. The history of solid mechanics is pretty interesting. It's all based in mathematics. It all came out of mathematics applied to situations that people were witnessing, and the things that stuck are the ones where people actually got it right. And so we still deal with those 150, sometimes 200 years later. Contact stresses are complex three-dimensional stress states. Their derivations come from that set of equations, which I showed you a couple of lectures ago, where we have constitutive laws, we've got equations of equilibrium, we have strain displacement relationships. Solving all of these over the regular geometries that we've been talking about with the ellipsoidal patches and whatnot creates this complex set of equations, and if you solve them, then you can get a solution for that stress state. And we'll briefly talk about what that solution looks like for this idea of a spherical rolling contact stresses, rolling meaning no slip. So the two surfaces do not slide past each other. If they slide, then that actually induces some sort of tangential stress, but here we're only going to deal with normal stresses. All right, so our archetypical case involves a sphere on another sphere, or sometimes in the math you can expand this to be a cylinder on a cylinder, or a sphere on a flat surface, or a sphere on a concave surface, and some of those are shown here. Imagine that this is extruded into the board, or this is extruded into the board, and now we have cylinders instead of spheres. We can also have a flat plane, or we can have a concave upward surface, and the mathematics will tell us how these things deform with respect to each other, but we will deal with the case of the sort of point contact with either a flat or a convex surface. The other thing to point out here is that if we have some load F that's applied, it has to be balanced by another load F. What happens is at the point of contact, we assume that there's some deformation, and we assume that deformation deforms the bodies into some contact patch radius. And that radius here is shown by a dimension A. Since these are two spheres, it would be circular. If these were two cylinders, this would be rectangular. Try and picture that one. So once all the governing equations are solved, the result for rolling contact is a complex 3D stress state that depends on the depth z, so that is the distance below our contacting surface, as well as Poisson's ratio, nu. And we'll talk about that in just a second. Now, remember, this is the spherical solution along the center line of a rolling sphere. So imagine this ball is rolling along, and the contacting surface beneath it is in contact with it only at the point at which it's rolling. And if we look then at our solution for the stress in the z state, the z direction, which is vertical up and down, we see, yes, it depends on our depth z in the numerator and in the denominator. And so there's some funky dependence there, which we'll tease out in a second. And we have our contact radius a. We also have sigma x is equal to sigma y, so that is our in plane, so horizontal and then into and out of the board, which also has our z dependence on the numerator and denominator, and also has Poisson's ratio. It's also interesting to point out that both of these have a leading constant term. So take a look at what happens when z goes to 0. Alrighty. If we work through those equations for the stresses and we integrate them over their contact areas, we can find that the maximum average values are strongly dependent on that contact area. Why? Because that's where everything acts. The contact stresses are here depicted as this semi-ellipsoidal distribution. At the center, we have our maximum, and as we go out to either edge around the boundary, either in our x direction or in our y direction, the stresses necessarily go to 0 when we leave the contact patch. So they have to approach 0. Yeah? So if we solve for our maximum pressure, we get 3/2 F over pi a squared. This stems from taking our force, integrating it on the surface over the ellipsoidal area to find that P max is related to our force by pi a squared times 2/3. And then we can use these two relationships to find that the average stress is F over pi a squared, so whatever the applied load is F, and the maximum is 3/2 P average. Now, this is actually important down here because what this shows us is that if you try and make an assumption that, well, I know what the force is acting on my body and I have a general idea of how much it's deforming to get my contact area, then I can find the average stress. And you may be able to do that from some measurements and some basic calculations, but the problem is that you will be underestimating the maximum stress by a great deal. Here, 50%. The max is 1.5 times larger than the average. So hold on to that because it's important. Okay, so we can compute the normal stresses, which are maximized at the surface, and z equals 0. And we can also compute the shear stress, which we'll see is maximized below the surface, z greater than 0. So what do we mean by this? Well, at the surface, we've got sigma x, sigma y, and sigma z. These are our Hertzian stresses that are applied by the contact condition. Since there's no shear, there's no sliding, this is a principal stress state. And if we look at z going to 0, our three terms marked here go away. Since these terms all have opposite signs of our leading constant term, we know that we'll get a maximum if we make sure that these do not diminish the stress values. And that leads us to having Z max is equal to minus P max, and sigma x and sigma y max are equal to P max times this ratio of our Poisson's constant. Okay. Now, there's also a shear stress induced from these principal normal stresses. Now, if we take away the caveat that this has to be at the surface, any place that we have an x, y, and z stress state, even if it's principal, we know from more circle or stress transformations that that has to induce some shear. We study this because we know that all metals fail in shear. So if we calculate the shear stress that comes from this sigma z max, from sigma z, sigma x, and sigma y, in the general case, here, we can find that it has a magnitude at its maximum, given by this expression. So 1/2 P max times this combination of our Poisson's ratios. And we know that that maximum occurs, we can compute that that maximum occurs at a z value given here. And if we put in Poisson's ratio of about 1/3, we'll see that we get a z value of 8 times about 0.63, 0.64. Which is kind of cool. So what does this mean? That means our shear is maximized below the surface, but our normal stresses are maximized at the surface. Alrighty. Why is this a critically important thing? Well, if we consider the depth, we see that the subsurface phenomena become important behaviors, important responses. So on the right, we're showing a plot of normalized depth, z over a. So how far into the body are we with respect to that contact patch radius? We normalize by a to give us a non-dimensional view of what's going on with respect to depth. We can also take the stresses that we compute, the shears and the normal stresses, divide by P max to get a normalized view of what's happening with respect to our stress. The first thing we might see is that as we get deeper and deeper, Z over A gets higher, the stresses all go away to less than 10% of P max. And this happens at about Z equals 5A. So our stresses trail off the farther we get from the surface. Maybe that's not unexpected. We also see that as z goes to 0, our normal stresses become maximized. We expected that one. But then that computed shear stress, we see it occurs at a maximum right here, like I was saying, about 0.63, 0.64 for steel-on-steel contact, or if you throw in Poisson's ratio of about 1/3. Why is that important? Well, it's important because some believe that the subsurface shear stress, because it's maximized at the location, becomes a nucleation point for failure in metals, because metals fail in shear. What also happens, if we have this beginnings of a shear failure, and then we add on to that these normal stresses which act at that point, if this is something that's rolling, meaning that that point of contact gets loaded, and then it gets rolled over, it gets unloaded, but then if it rolls back to that same point, or if there's something that's loading it, releasing, in a normal stress fashion, here compressive stresses, then that can lead to fatigue crack growth. And we have this fatigue failure phenomena that's added on to our initiation of failure due to shear. And once this occurs over time, we can reach a limit cycle in which we can predict where these things will fail. And that's one of the ways that people begin to analyze ball bearings or any sort of rolling metal structures. So it's kind of cool that the subsurface stress leads to failure under the surface. It's exacerbated by normal stresses, and then it's evidenced by the failures that we see cracking or pitting on the surface after the fatigue limits reached. Well, thank you for participating. Thanks for joining in. Hopefully you've learned a little bit of the basics and the fundamentals of Hertzian contact stress. Remember, this is for a sphere rolling on a surface, either another sphere or a flat surface, with no slip, meaning we've got that single point of contact and no translational forces, no transverse forces, no shear stresses developed at the surface. Thanks for participating. Like I said, hope you're having a good day. We'll see you next time in the next lecture, and you can use this information to better understand what's going on with the plier model, because you may see that we're able to pick up in our analysis some of these surface and subsurface phenomena. Thanks, and take care.